Hi, can you hear me okay? Okay. Before I start, I'd like to spam you very briefly about a conference that I'm organizing. It's called Lambdale. It's a functional programming conference in a pub in London in September. The CFP is open. Come and talk to me afterwards if you're interested. Okay, so I'd like to tell you a little bit about reinforcement learning, which is it's a machine learning paradigm that's become quite popular in the last few years. It's had some very famous successes. This is a good example. This image is, it's a game that AlphaGo played against Lee Sedol. It's the first game they played in a series of 5, and this is the point at which Lee Sedol resigned. So it was a very groundbreaking moment in reinforcement learning and machine learning and Go. So this is an example of the kind of powerful stuff you can do with reinforcement learning. So today, we're not going to build this. This is quite advanced. But I'm going to give you an introduction into what reinforcement learning is, how it works. As we go along, we're going to look at how to implement it from scratch in Scala. And there will be a few shiny demos in Scala.js as well. So this is reinforcement learning in a nutshell. So you have your agent. This is the thing that's doing the learning. And your agent is interacting with an environment. So your environment, as you can tell from the diagram, it kind of looks a bit like a state machine. You can just think of it as that. And it interacts with the environment by taking actions. There's usually a predefined list of actions it can take. Say, if it was navigating in a maze, actions would be like turn left, turn right, go straight. And then your environment responds to that by saying, okay, based on that action, you are now in a new state, and I give you a reward. And the reward might be positive, it might be negative, it might be 0. So that's it. It's a very minimal framework. It seems quite abstract, but it turns out that you can frame an awfully wide range of problems in this paradigm. And if you can frame your particular problem in this way, then you get access to a huge wealth of mathematical research over the last few decades on reinforcement learning. So we're going to have a look at how you implement something like this in Scala. There's two kind of standout features of reinforcement learning that I think are really interesting, why I got interested in it. And the first one is that it is unsupervised learning. So generally, if you think of machine learning, you think of like training sets. You build like a labeled training set of here's some inputs and here's the correct answers based on those inputs. And then you use those to train your neural network or whatever. And then you might have a test set as well to check that it hasn't overfitted. But anyway, you generally have to come up with a very large data set which has been curated by a human, and you use that to train your machine learning model. And that is a lot of effort, and it doesn't scale necessarily. So the nice thing about reinforcement learning is that you don't need to do that. You just you start with basically a random agent, completely dumb. You just kind of throw it out into the environment, and you let it fend for itself, and gradually it will learn for itself, and it will get smarter. And then the other thing that is interesting about reinforcement learning and is quite unique to it, I think, you don't see elsewhere in machine learning, is this idea of a delayed reward. The reward that you get might be deferred. So, for example, if your agent is trying to solve a Rubik's Cube, trying to solve a Rubik's Cube, and it does say, it twists the cube this way, and then this way, and then this way, and then this way, it does say a sequence of 20 moves. Eventually, it solves the puzzle and it gets the reward. But how can you say which of those moves were actually responsible for it getting the reward and solving the puzzle? In a sense, they were all responsible, but how do you kind of assign credit to each of those moves that you did along the way? And reinforcement learning has a good kind of mathematical theory behind it, which can help you to answer some of those problems. So let's have a look at the environment first, and then we'll move on to the agent. So the environment, as I said, it's kind of a state machine. If we want to be more technical about it, it's actually called a Markov Decision Process, an MDP. You'll see that a lot in the literature for reinforcement learning. We won't go into too much detail about what that means, but it just has to satisfy certain properties. But you can think of it as a state machine, and it provides answers to two questions. Given that the agent is in a current state, S, and it takes an action, A, what state does it move to next? And also, what reward does it get along the way? So what state does it go to, and what reward does it get? And both of those, they're called the transition function and the reward function. Both of them can be stochastic in general, meaning they follow some kind of probability distribution. So even if you're in some state and you take some action twice, that you might get different results the first time and the second time. So an example of a very simple Markov decision process might look a bit like this. So it's got 5 states, S1 to 5. Let's say your agent is in state S1. It takes action A1, so it goes up that arrow. It gets a reward of 5, and it ends up in state S2. So your agent will just kind of work its way around this state machine, potentially forever. Although in this case, we have this state down at the bottom right, this S5. This gray box means that it's a so-called terminal state. So if your agent ends up in this state, that's the end of the episode, and you just kind of stop there, you reset, and start again. Depending on what kind of problem you're trying to model, you may have terminal episodes, or you may just carry on looping forever. So, for example, if you are trying to use reinforcement learning to trade stocks and shares, that doesn't really have an ending. It just carries on from now until the end of time. So there won't be any terminal states. Every day you'll end up in a new state. Your rewards might be like how much profit you made on the previous day or something like that. And then it carries on forever. So that's called a continuous problem. But if you have terminal states, that's an episodic problem. And it's worth pointing out that this is the environment, the dynamics of the environment, but the agent in general has no knowledge of this. So this is a complete black box to the agent. It doesn't know that if it's in S1 and it takes A1, it'll end up in S2. It has to find that stuff out for itself. So let's have a look at how we might model this in Scala. I've made it a trait environment. I've made it generic in the type of states that you deal with and the type of actions that your agent can take. Because no matter what particular problem you're trying to solve or trying to model, the interface of the environment is never really going to change. It's going to be polymorphic in those things. So the most important function your environment needs to offer in its interface is this one, which I've called step. So given that your agent is in a certain current state and it takes a certain action, it needs to return 2 things. It returns the next state that the agent goes into, and also the reward that it wants to give to the agent. What is a reward? A reward is just a number. So in reinforcement learning, your state might be very complex. It might be like a feature vector with hundreds of dimensions, but your reward is always just going to be a numeric value, which might be 0, it might be positive or negative. And then there's one more thing it needs to tell us, more of an implementation detail really. It just needs to tell us whether a given state is terminal so that we should stop the episode. So the agent is the thing that we're, in a sense, more interested in, because this is the thing that does the actual learning. And this thing, all it can do is take actions. So at every time step t, the agent is in some state. Currently it's in a state. It chooses an action. It gets told, you're now in this new state. You got this reward. And then hopefully it will actually do some learning at this point. This is its one opportunity to use this new information to learn something and get smarter. Again, we'll model this in Scala. So I'm going to separate the behavior from the kind of internal data. So we'll just look at the behavior of the agent first. So it's polymorphic in its data, the type of states and the type of actions. because the data, the shape of your data will depend on what particular machine learning or reinforcement learning algorithm you're using. So we'll come back to that later once we've actually chosen an algorithm. And it just has one thing that it needs to do, which is choose action. So given its current agent data, the current state that it's in, and a list of actions that it's allowed to take, it needs to choose one. So it needs to return an action, but it also needs to return one more thing, because remember, this is the point where it actually does some learning. So once it's chosen an action, we will apply that action to the environment, which will tell us, okay, you're now in the next state, here's your reward, and it needs to do that it needs to use that information to do some learning, so it needs to return an updated version of its agent data. That's where it stores all of its learned information. So it's going to return a function from action result to agent data, where the action result is the reward and the next state. So that's the environment and the agent, and then we just need a little bit of glue code to wire those two things together and make them talk to each other. So I call that the runner. So this is kind of like the edge of your program where you're wiring things together and actually running the loop. So the runner is pretty simple. We start off with just initial agent data. It could be like all zeros or just random numbers, just a very dumb agent. You start with an initial state. You might just randomly place it in one of the states in the state machine. And then at every time step, it kind of acts as a go-between between the agent and the environment. So it'll ask the agent, can I have an action, please? It'll take that over to the environment. It'll tell the environment that. That'll tell it the new state and the reward. You tell that to the agent. The agent does some learning and returns an improved version of its agent state. And then step 4 will depend on what your application does. So in my case, I'm just going to show you demos. So I'm going to be just updating the UI at that point. But you might be like steering a helicopter or trading stocks and shares or launching missiles or whatever your agent is supposed to do. So just to go through in code what I said on the slide, there are some vars on this slide. I'm very sorry. But remember, this is the very edge of the program. And you could use a state monad if it makes you feel better. So this runner will have a function called step, which just does what I said on the previous slide. So it asks the agent to choose an action. It tells that to the environment. It calls the agent's update function to get the new version of the agent data, and then it updates the UI. So we can see all of this in action in the first demo. If I can find it. So this is a so-called grid world problem. These are very common in the reinforcement learning literature. They're just a very kind of simplified version of the world, which makes it easy to use as a test bed for reinforcement learning algorithms. So your agent, in this case, is the little red dot, and its job is to wander around the world, the grid world, and there are certain rules, the dynamics of the environment. So if it can move up, down, left, or right. If it tries to move off the side of the board, then it gets no reward. -1 reward, and it stays where it is. If it goes just to a normal place, like say if it went down from where it is currently, gets no reward and nothing happens. It just moves there. And then there's these special A and B. So if it's on A and it moves in any direction, then it magically teleports down to A prime and it gets a reward of 10. And then similarly for B, but it gets a reward of 5. So if you think about this for a few seconds, it's pretty clear that the optimal policy for this agent, if it wants to maximize its reward, is just to make its way over to A as quickly as it can and just keep going to A, jumping down to A prime and then going back up to A and looping forever. So that's what it should learn how to do. So we can see it, I'll just run it for a couple of time steps. It's just moving around randomly at the moment. It doesn't have any knowledge at all. It's just exploring. Okay, it's found B, so then it teleported down to B prime, and it got a 5 reward. So it's found a local minimum there, so it can potentially get stuck. It might be satisfied with that and not discover A for a while. But the important thing is that it's got this element of randomness. It's always exploring, so it's guaranteed to visit every single cell an infinite number of times. So eventually it is guaranteed to find the optimal policy. So we can just let that run for a while. And you can see that it's updating some mysterious numbers down here. We've got a minus 0.9 here. I will explain what those mean later. For now, you just have to trust me that this thing is actually doing some learning. It's quite mesmerizing to watch, but I should probably move on. So that is Grid World. Oh, it found it. Yay. Okay, so it kind of looked like it was doing some learning, but how was it actually working? How does it learn? In order to answer that question, I need to take you through quite a lot of jargon, some basics of reinforcement learning theory. So we're going to look at each of these in turn. State action values, policies, prediction and control, model-free and model-driven techniques, exploitation versus exploration, and bootstrapping. And then finally, once we've gone through all of those, I can reveal the name of the algorithm that it's actually using, and then we'll look at that in more detail. So state action values, these are the mysterious Q values that were on the page just now. I can show you those again. So these QSA, these are called state action values, and this is the value, well, the agent's estimate of the value of being in some state S and taking some action A. So for each state S and each action A, Q of SA is the estimate of the value of being in state S and taking action A. And then Q star is the optimal value. So Q is the estimate, what the agent thinks is the correct value, and then Q star is the optimal value, the best one. What do I mean by value? The value is the total return of all rewards from that point onward. So ignoring everything that's happened up till now, from now, if I start in state S and I take action A, from now until the end of time, how much reward do I think I will get? For continuous problems like this grid world one that don't ever end, you have the problem that your total rewards end up being infinite. They just get bigger and bigger and bigger. So you have to do some discounting. You have to apply a constant to kind of trail off as you go further into the future. So a policy is what the agent is trying to learn. So the policy says, if I'm in some state S, which action should I take? It's like a decision-making function. If we have this state action value function, QSA, then from that you can just trivially make a policy. So I've made my super awesome policy, which says, if I'm in state S, just choose the action A with the highest Q value. So if I've discovered, if my estimate of the action value of moving right is 9.3, then if I'm in this state 1.1, then I should always move right. That's my policy. So the job of the agent, what it's trying to do by learning, it's trying to learn an optimal policy. And learning an optimal policy in general is quite a difficult problem, but you can split it up into two easier problems. Namely, evaluation, also called prediction, which is given some policy, which we usually call pi, given some policy pi, how good is that policy? What value can I get out of that? What reward can I get? And then the other problem is, given this policy pi, can I do improvement, also known as control, to just make it slightly better? Can I incrementally improve that policy? And if you can do both of these things, then that naturally gives you a pretty simple strategy that you can use for learning. You start with just a blank policy, might be random, a random set of Q values and a random policy, and then repeatedly you evaluate that policy, see how good it is, and then do something to make it slightly better. And then you just repeat that, and your policy gets better and better and better. And given the right mathematical conditions, your agent is guaranteed to eventually learn the optimal policy. It will find the correct answer. Next up is model-free versus model-driven techniques. So potentially, you could have a model of the environment that you program into the agent a priori before it starts running. So you could tell the agent, you're going to be in a grid world, these are the dynamics. If you're in this state S and you took this action, you'd end up over here and you'd get this reward, and so on. So you'd have a model of that whole state machine in the agent. And if you did that, then your agent would be able to do kind of planning and dynamic programming and things like that. And potentially, it would be able to learn very quickly. In practice, this doesn't really work out in many cases, usually because the environment is just so complex, there's so many states, that you can't really do any substantial calculations, any planning on the model. Even if you can fit the model in memory, it's just so big that you can't really make any headway with it. So in today's talk, everything is going to be model-free. So the agent has no understanding of the environment's dynamics at all. It's a complete black box. It's just kind of, it has to do trial and error. It has to wander around and explore and gradually learn about the environment. Exploitation and exploration. So you could see in the demo just now that it was moving around kind of randomly. It was exploring the state space. But as it learns, it will hopefully get smarter. It'll start from completely no knowledge at all, but hopefully it'll learn some useful things about the environment. So at some point, it should start to exploit that knowledge that it has. It should be reasonably confident that I have the correct answer, so I should probably just do what my policy tells me to do. But on the other hand, there's an opportunity cost to that. You might miss out on this amazing state over here that you don't know about because you haven't explored it yet. And this is a kind of dilemma that we go through as humans as well. When you go to your favorite restaurant, you might go for the hamburger that you always have because you know it's delicious, but then what about that other thing that you've never tried before? It might be even better than the hamburger. And there's a lot of different ways that you can deal with this trade-off. The simplest one that I've used is called epsilon greedy, and it's really trivial. It's just you follow your own policy most of the time, but epsilon% of the time, you just pick a random action instead. This can be dangerous if the impact of choosing a wrong action is very high. Say you're controlling a robot and your robot falls off a cliff because it chose the wrong action. That's quite bad. But in this case, we're just moving around a grid world, so we're probably safe. Finally, the last bit of jargon I have to get you through is called bootstrapping. So this is the idea of kind of building castles on sand, I suppose, basing estimates on other estimates. So imagine this state machine. These numbers are all just made up. They don't mean anything. But imagine that your agent had this kind of estimate of the state machine. It's built up these estimates. All these question marks represent that this is an estimated value that the agent has guessed. So say it's in the 3.5 state, and it moves up to the 7.9 state, getting a reward of 4 on the way. Maybe it can use that estimate, that 7.9, combined with the reward it got to update the estimate to 3.5 using some formula. So this idea that you can use estimated values to improve your other estimated values is called bootstrapping. And again, given the right mathematical conditions, miraculously, it actually converges to the right answer. So just to recap, because we went through quite a lot there, state action values, those are the Q values, the Q of S and A. That's the value of being in state S and taking action A. Once you have state action values, you can use those to create policies. You can iteratively use prediction and control in order to improve your policy and learn the optimal policy. We are going to be talking about model-free techniques, so everything is a black box to us. We are going to use epsilon greedy to trade off exploitation and exploration, and we are going to be doing some bootstrapping. So, after all that, I can reveal that the algorithm that I implemented for this is called Q-learning. This is a model-free algorithm. It uses epsilon greedy or some similar exploration technique, and it does bootstrapping. Now, Q-learning is quite an advanced technique. If you read a textbook on reinforcement learning, it'll come up kind of halfway through. There's quite a lot of mathematical theory behind it, but actually, implementation-wise, it's pretty simple. It comes down to one quite simple update rule. So I'm just going to shove this in your faces and then unpack it. So QST80, so this is the action value, the Q value of the state that you were in at time t and the action that you took at time t. And we want to update that. We want to improve that value, our estimate of that value. So we're going to update it by moving it a little bit in the direction of the reward that we got. So that's RT plus 1, plus some multiplier times the maximum Q value in the next state that we went to, minus the original Q value. So if you look at this diagram, it might make a little bit more sense. So we were in state ST, we took action AT, we got reward RT plus 1, we moved into state ST plus 1, and then from state ST plus 1, there's a few different actions that you can take. So there will be a few different Q values in that state, one for each of the actions. And we'll take the maximum of those, and we'll use that to update our estimate of ST, or sorry, our estimate of the Q value for ST80. So that is Q-learning in one line. And we'll look at how to implement that in Scala now. So now that we know which algorithm we're using, we can write the agent data, which I skipped over earlier. So we've got this case class Q-learning. Again, it doesn't matter what the type of state and the type of action is. So it's generic in those. It's got these three parameters that you can tweak. I won't really go into them. But then it's got Q, which is its map of, its kind of lookup table of state action values. Now we can implement the agent behavior. So this is our implementation of the agent behavior trait that we defined way back at the start. So we've got our update function. It's just a type alias to say, given the result of taking an action, I'll give you a new Q-learning case class. So given the agent data, which is your Q-learning, and the current state and the list of actions you can take, so it looks up the Q value for the current state. It does epsilon greedy to decide which action to take. So it's looking at both the Q values for each of the actions for that state, and also using some randomness to decide, maybe I'll just take a random action. And then the update function that it returns looks like this. So given the action result, it works out the maximum Q value from the next state, the state that it moved into. That's just looking it up in the Q lookup table. Then it does the update rule that we looked at in mathematical notation just now. That's just written in Scala. And then it just returns a copy of the agent data with the Q lookup table updated appropriately. So that's Q-learning. Surprisingly small amount of code for such a powerful technique. But one problem that you may have wondered about is this Q This queue here, in the case class, this map of maps, that's potentially going to get very large depending on what kind of problem you're solving. If your state space is big, then maybe this won't fit in memory, or maybe it'll be so big that you won't actually ever explore enough of it to learn anything, unless your agent runs for 100 years or whatever. You might learn very, very slowly because your state space is too large. So when we start looking at more interesting problems than just this grid world, when we look at real world problems that we want to solve with reinforcement learning, we often have to do this kind of shrinking of the state space. So the environment state will be huge because it has some very complex dynamics, but we will kind of bucket that or quantize it into smaller pieces, and the agent will look at this kind of simplified, rough view of the agent state, and that's what it will use for its Q learning. And this mapping can be very difficult to define in an effective way, but if you can define it, then this can be quite an effective technique. So we're going to look at an example now. So you'll end up with this state conversion, which just says how to convert your environment state into your agent state. And we're going to look at an example of a case where this is necessary. So it's time for our next demo. So this is the so-called pole balancing problem, or pole and cart problem. And this is a very famous example from the reinforcement learning literature. So the idea of this is that you've got a cart, the blue thing in the middle, and on there is a pole that's balanced perfectly at the moment. And your job, your agent's job, is to move the cart left or right in order to keep the pole balanced. So if the pole topples over more than 12 degrees, I think, in either direction, you lose. Game over. And also if you hit the walls on either side, you lose. And the interesting thing about this is that there's very, very little feedback. So on an ordinary time step, you get no reward at all. You only get a reward of -1 if you actually fail. So if the thing topples over, somebody hits you with a stick and says, you failed, you get a reward of -1, and you start again. So just to prove that this is a reasonably difficult problem, I made a version that you can play yourself. So if I lasted 0.18 seconds. Nice. If I do this really quickly, I can last 2.5 seconds. So obviously it's not that hard for a human to do. You just toggle left and right. But for an agent, this is actually a reasonably interesting problem. So if we just make it take a couple of steps, you can see it's moving around. We'll run a couple of episodes. So just to remind you that this is a model-free technique, so the agent has no idea about the dynamics of the environment. It doesn't know anything about poles or carts or angular velocity or any of that. All it knows is somebody is telling me that I have to choose left or right, and occasionally they hit me with a stick and give me a reward of -1. But somehow, based on just this feedback, it learns remarkably quickly. So if we let it run forever, then you can see that it's gradually getting smarter and smarter. So it's done 14 episodes now, 15. All right. So if I leave that running in the background while I carry on, and we can come back to it later if I remember, you should see that it basically solves the problem. It can go for hours and hours.
Then you saw where it's a combination of it starts with no model, but the next episode has a model.
Yeah, well, not a model exactly. It has Q values.
Okay, Q values.
Yeah. Yeah, I can show you if we scroll down. These are the Q values. So it's a lot more. There's a lot more states than there were in the grid world, but there's a lot fewer states than there are in the actual environment. The environment is continuous, like it's got, well, continuous to the extent that Java doubles are almost continuous. So it's measuring the angular velocity, the velocity of the cart, the position of the cart, and the actual angle of the pole at any time. So those four things make up the dynamics of the environment. And then the agent state is a kind of quantized, smaller version of those things. And you can see that it's gradually updating its Q values. Oh, it's getting pretty smart. It's done nearly 17 seconds now. So I need to go back to my slides. So that is mostly all I have. I think I'm nearly out of time. I just have one more demo, but this one is marked as homework. And the reason for that is that I've implemented an agent to play Pac-Man, but it's completely terrible. So I need your help to improve it. So if you're interested, you can come and talk to me afterwards, and I'll explain how you can check out this code and play around with it. There's a nice kind of training harness that you can use to test how good your Pac-Man is. But we can at least see what it looks like. So with the caveat that this thing is not very good at playing Pac-Man, you can at least see that it's doing stuff. And the reason it's not very good is that the state space of Pac-Man is huge, and currently it's very naive. It's taking the environment state as is and using that as its agent state. So ideally, you'd come up with some smart encoding of how to shrink the massive environment state into a useful state, or I guess you can think of it as a set of features that the agent should care about in order to get better at playing Pac-Man. So that might be like the location of the ghosts and how close it is to a piece of food in each direction, that sort of thing. And if you want to get really fancy, then you could start doing function approximation using neural networks, start doing some deep reinforcement learning. But that's definitely outside of the scope of this talk. I've lost my mouse. Okay, so there are some next steps that you could take to improve Pac-Man or to improve any of the performance of any of these demos I've showed you. You can do some simple things to improve your policies, make them a bit smarter. So, for example, the epsilon greedy that we're doing, that uses a fixed epsilon. So even after your agent has been learning for a long time and it's got really smart, it's still going to just choose a random action 1 epsilonth of the time, even though it should have more confidence in its own judgment. So what you can do is to decay epsilon over time, assuming that your agent is going to get smarter. And there's also different policies you can use there. There's, softmax is a commonly used one. You can also choose completely different learning algorithms from Q-learning. So there's a whole zoo of learning algorithms out there. There's TD lambda, Q lambda, and so on. And then if you want to start looking at really interesting real-world problems, then generally you're going to have a large or possibly infinite state space, which means that this kind of table lookup-based approach just doesn't scale at all, and you'll need to start looking at function approximation, and that's where neural networks and deep reinforcement learning comes in, and that's where it gets really interesting. If you want to learn some more about this, this first book, Reinforcement Learning and Introduction, this is like the Bible of reinforcement learning. It's by Sutton and Bartow. It's a classic, but a second edition just came out last year, I think, in the last few months. So it's a classic, but also up to date. It's really good. There's also a whole lecture course on reinforcement learning by David Silver from DeepMind that's available on YouTube. And they've also recently released another lecture course, which is like an advanced version of that. It's much more, goes much deeper. So thank you for listening. The slides are online, the demos, if you want to play with them, and all of the source code are all on there. I don't know if we have time for questions, but you can come and talk to me. Thank you.